Welcome to ASM Tower software tutorial video. In this video, we will learn how to model monopiles to support your structure. ASM Tower is capable of designing both rigid and flexible monopiles. For this example, we have a 60 meters self-supported tower and we need to define monopile to it. The monopile is designed to withstand axial compression by bearing on the soil layer at the end of the pile, in addition to the frictional resistance with the surrounding soil. Conversely, when subjected to tension, the monopile relies solely on frictional resistance. When it comes to lateral loading, the monopile resists it by bearing on the lateral soil layers. First, we need to solve the tower to get the reactions ready. Click Analysis button. Click OK. Click Done. From Lattice Tower Group, open Monopile dialog box. Enter the name of the foundation. Select Leg Force tab. Check Automatic Reaction box, to let ASM Tower reflect the reactions from tower to the monopile automatically. Load combinations have been added, with each combination being categorized as either a service load or not. For ultimate strength load combinations, don't check this option to let ASM Tower checks the lateral resistance not to exceed the allowable limit for limit state load combinations. And check it for the serviceability combinations to be compared to allowable limit for serviceability combinations. Select Geometry tab again. Design code, number of supports and towers face width are disabled and ASM Tower got their values from project input, because we chose automatic reactions in Leg Force tab. Select the section type either circular or square. This is the diameter of circular pile or the width of square pile. Let's leave it 0.8 meter. The length of the monopile is measured from the end bearing point to the top point of the monopile located under the structure. Set length equals to 15 meters. Define the number of longitudinal bars required to resist moment and tension in the monopile. Start by setting the number of bars to 10. Define the spacing of stirrups reinforcement that will resist the shear force in the monopile. Set the spacing equals to 100 mm. Note that the straining action in the monopile isn't calculated yet, and it will be calculated after performing the design. Check Master Foundation box to show the monopile in 3D view. It doesn't affect the calculation. Select Parameters tab. The reduction factors are used in the terms of calculating the soil resistance for friction, bearing and lateral. The values are filled according to the default values of ASHTO. And soil lateral reduction factors value is filled according to the default values of TIA-222. You can also change these values according to his specifications. As per ASHTO standard, it is usual to neglect side resistance in the top 5 feet of the monopile. This approach accounts for the potential reduction in side resistance due to soil expansion and contraction caused by wetting and drying, as well as freezing and thawing. Similarly, the lower part of the soil, which equals to the diameter of the monopile, is also neglected in the design process. This is because the soil resistance around the base of the monopile is influenced by tensile stress resulting from the downward movement of the monopile, which can lead to cracking of the soil. The ASHTO requirements do not include any explicit provisions for neglecting soil lateral resistance. Choose this option, to let ASM Tower calculate the resistance distance which will be ignored according to considerations of ASHTO automatically. You can choose manually to set resistance distance which will be ignored from top and bottom of the monopile in the cases of friction and lateral separately. The top distance is measured from the ground level and the bottom distance is measured from the end bearing point of the monopile. It is possible to specify different distances to be ignored at the top and bottom of the monopile for both friction and lateral cases. Two types of lateral loads can be applied to monopiles, static and cyclic. The choice of the load type depends on the actual applied load on the monopiles. If a cyclic load is chosen, you can input the number of cycles. The soil lateral resistance will be decreased in case of cyclic load, however friction and bearing resistance won't be affected. Select the monopile shape that ASM Tower will consider it in the soil lateral resistance calculation of the square monopile, regardless of the selected shape in the Geometry tab. The lateral resistance of soil for a square monopile is higher than that for a circular monopile, because shearing stresses could act along the back half of the sides of the square section. If square option is selected, ASM Tower will account for the monopile's soil lateral resistance increment. Circular option can be used as a more conservative option. Open Soil Layer tab. You can define the depth of groundwater by checking this box and input the value of water depth. Set it equals to 8 meters. ASM Tower will automatically assign the suitable soil density depending on its elevation. Above the water table, density is defined as in-site soil density, while below it, it is defined as saturated density. The influence of frost depth on calculations is primarily limited to cohesive soil. In cohesive soil, when the water within the soil freezes, it causes an increase in the size of water particles and forms cracks within the soil. When the frozen water thaws, these cracks may be filled with air, resulting in a reduction of the soil's friction capacity. At the frost depth, the soil capacity is typically neglected in calculations due to the compromised soil properties caused by the freezing and thawing process. The frost depth is measured from ground surface and its value has to be positive. Set it equals to 0. Define the name of the soil layer. Top elevation of soil layer is measured from ground level to the top of soil layer and its value should be positive. Top elevation of the first soil layer shall always start from 0. Soil parameters should be obtained from soil reports. If no specific values are available, you may utilize the values assumed by TIA-222. Now we need to define the soil density in the two cases in-site and saturated density. Observe the picture to figure out what is the difference between them. The soil in its original form consists of three components: soil particles, water and air. When the soil is under ground water level, it will turn into saturated soil, as the water replaces the air and increases the soil density. That means that saturated soil density is always greater than the original soil density. Let's assume the soil density is 16 kN per cubic meter. And the soil saturated density is 18 kN per cubic meter. In the context of soil classification, two main types are commonly referred to: cohesive soil, also known as sea soil, such as clay, and cohesion-less soil, also known as phi soil, such as sand and gravel. These different soil types possess distinct characteristics that significantly impact the design of monopile foundations. Among the parameters that differentiate these soil types, one crucial factor is the value of N60, which represents the corrected standard penetration value. Several different types of SPT hammers are used to conduct standard penetration tests. Their varying efficiencies influence the N value. That's why we need to calculate a standardized value of N, which is N60. N60 value is calculated by multiplying SPT N value by the efficiency of the used hammer. Remarkably, N60 and phi are closely linked, meaning that either value can be driven out of the other value by approximate equation. In the case of phi soil, N60 plays a vital role in calculating friction and bearing capacity. As the first layer is sand, we don't have C value. Define phi value equals to 30 degree. Put N60 value equals to 0 to let the software calculates it approximately depending on phi value. Choose the color of the soil layer. PY curve shows the relation between the displacement and the soil capacity. It represents the soil behavior under the lateral load. We have four options to choose from: sand reese, soft clay, stiff clay with free water and stiff clay without free water. We will choose the first option, sand reese, as our first layer is sand. Epsilon 50 represents the strain corresponding to a stress of 50% of the ultimate stress. It is typically required for cohesive soils. In ASM Tower, if this layer consists of cohesive soil, the epsilon 50 value can be assigned equals to 0, and the software will automatically estimate it. However, in the case of a cohesion-less soil layer, epsilon 50 is not necessary. We will keep it blank. K factor is the initial soil modulus, represented by the slope of initial part of the PY curve. K factor affects the lateral resistance in sand and stiff clay without free water. K value can be left equals to 0 and ASM Tower will approximately calculate it. The friction stress and bearing stress values can be manually input if they are given in the soil report, or if the user prefers to calculate them using a method other than the one provided by ASM Tower. The friction stress value will be multiplied by the side area of the monopile within the layer, while the bearing stress will be multiplied by the cross-sectional area of the monopile. This allows for the calculation of the soil's capacity using the user's chosen method. Define second layer, which is cohesive soil, in the same way that we have explained for the first layer, except the cohesion is set equals to 100 kPa, friction angle equals to 0, and for PY curve select stiff clay. In addition to the previously mentioned soil layers, a third layer can be defined as sand soil. Furthermore, the option remains to define additional layers as per the previous illustrations. Click Add. You can add many monopile foundations with different parameters in the same file. Click OK. The color boxes at the top right corner serve as an indicator for the initial design status. You can see that the color box of soil down is red, which means it is not safe and its ratio is between 1 and 1.4. Due to the soil down is resisted by the bearing and friction soil resistance, it is affected by the diameter and the length of the monopile. So let's try to set the diameter equals to 1 meter. You can see the box of soil down is changed to yellow, that means it is safe. But the minimum reinforcement color box is now turned to red as the steel ratio of the longitudinal bars is less than the minimum accepted ratio. So, let's increase the number of longitudinal reinforcement bars to be 11 bars. You can see the box is turned to yellow. We will start the design with this minimum required steel area, and if necessary, it can be increased based on design results. The software will perform the checks and provide a detailed output report. The boxes are colored according to the design conducted at the top section of the monopile, where the reactions are applied. However, if the critical section of the monopile undergoes changes during the design process, the design result might change. Click Update. Click OK. Click OK. Click Update to refresh the graphics. You can see the piles are added to 3D view. Reopen Monopile dialog. We have already updated the reactions and no need to resolve the tower. So, click Cancel. Click Design to perform the foundation design. The report is open. Here is the executive summary for the monopile design with the corresponding utilization ratio. And monopile sketch showing its diameter, elevation and soil layers. The compression capacity of the monopile is a result of the combined bearing at the tip of the monopile and the friction between the monopile and the surrounding soil. This graph illustrates the relationship between displacement and the vertical capacity of a monopile. The total capacity of the monopile is determined by the combined friction capacity and bearing capacity at same displacement. The maximum friction capacity occurs at small displacements, while the maximum bearing capacity occurs at larger displacements. That's why the maximum total capacity may not necessarily be the summation of the maximum friction and the maximum bearing capacities. The uplift capacity is determined by the summation of the friction between the monopile and the surrounding soil and the own weight of the monopile. Another graph depicts the side friction diagram along the monopile under both downward and uplift forces. The solid line represents the maximum friction capacity that the monopile can reach, while the dashed line represents the friction capacity of the monopile based on the displacement resulted from the finite element analysis. The graph presented displays the interaction diagram for combined compression and bending moment, as well as for tension and bending moment. Within the graph, there are 2 points of interest. The upper point represents the design status corresponding to the maximum compression and bending moment, while the lower point represents the design status for the maximum tension and bending moment. It is important to note that if both points fall within the bounds of the interaction diagram, it indicates that the design is considered safe. Additionally, a graph displays the distribution of lateral soil pressure along the monopile at different elevations in 2 cases, non-service loading and service loading. The graph shows that the lateral soil pressure in clay layers is greater than that in sand layers. The following graphs represent the internal forces diagram at a specific load combination, which is determined to be critical for downward force. In the case of a tower, the moment at the top of the monopile is dependent on the type of tower support. If the support is hinged, the moment at the top of the monopile will be 0. However, if the support is fixed, the moment at the top of the monopile will have a non-zero value. On the other hand, in the case of a pole, the moment at the top of the monopile always has a non-zero value. It is equal to the moment at the base of the pole, and it gradually increases slightly until reaching the maximum moment. In both cases, the maximum moment occurs at the point of zero shear. Also, you can see that the maximum shear force in the monopile is much greater than the horizontal reaction of the pole. The shear force increases gradually until reaching the maximum shear value. Similarly, there are separate internal forces diagrams for the critical load combination associated with uplift forces. Furthermore, the provided graphs display the maximum deformation diagrams for the monopile, including lateral displacement, sway, and twist angle in 2 cases, non-service loading and service loading. Close the report. Thank you for watching.